Hi everyone, how are you doing? Today we're going to be working on a new fluid mechanics problem for homework 2 part 3. This is going to be a multi-part video, so we'll start the problem here on the board and then we'll go back to the computer desk and write some code to solve the equations we're going to come up with in the first part of this problem. And you'll see why here. It's not going to be fun to solve by hand. So the problem we're kind of interested in today, and I'll get more into the specifics of it as we get towards the computer. But in general, this is the one we're going to be solving. It's how far does water encroach into a diving bell with known material and dimensional properties at a known depth underwater? Okay, so if you've never seen a diving bell before, it's effectively a cylinder turned upside down and you push it underwater while it's filled with air, and it allows you to access the floor of a lake or an ocean or something like that, without having to pump water out. Really, you're just keeping the air under there. The problem with this is as you go deeper and deeper and deeper underwater, that air inside the diving bell experiences more pressure from the water trying to push its way back in, and so the air actually compresses inside the diving bell, meaning the water is allowed to encroach up into it. And that's kind of what we're interested in today, is how much does the water encroach into the diving bell when we know how deep we're going to be putting our diving bell in. It's going to be important for people using these diving bells. They don't want the water up to their heads while they're trying to work under there. Is it at a manageable level or is it too far? So that might be some of the application of this problem. So just like we do before, we're going to start with drawing a nice picture out for us. This is going to help us kind of see the problem a little bit better. So we have some, body of water here, and we're going to stick our diving bell, and we're calling our diving bell for the purposes of this example a cylinder. So we're going to stick this thing underwater, and I'll just draw out here's our little diving bell, okay, and it's hollow up inside, so you might have little guys standing in here like this, right? Okay, so what does the problem tell us? Well, we know the depth that we're trying to stick our diving bell underwater to. Okay, so we might call this a depth of D. And we also know the material properties and the dimensional properties of the diving bell. This will come into play when we're actually trying to solve the problem on the computer. But for now, I'm just going to keep it simple and leave those properties off the board. We'll just use variables to express them rather. So we'll call the diving bell having a height of h, a radius of r, a material thickness of T, and a material density of rho. We'll say rho sub s. You'll find out later it's going to be steel. It's a steel diving bell. Okay. Additionally, some of the other things that we're going to draw in here that'll help us solve this a little bit better. Like I said, there's going to be some air inside this, but as you go deeper, the water is allowed to encroach in the diving bell. So let's say it encroaches, some amount like this. And we're going to call this distance Z. This is what we're going to end up solving for, is this Z value at the end of this video. And what else do we need? I think that's really all we need. That should be enough to get us started. Okay, so the way we're going to go about solving this problem is we're going to eventually have multiple equations that we're going to have the computer solve for us. What are those equations going to be? They're going to be a force balance equation and a pressure balance equation. Okay, so the forces on this diving bell should equal 0 if it's stationary at the bottom of this lake or whatever. And then the pressure here at the surface also should be, there should be an equivalent pressure system here because it's not moving. So we're going to derive, let's do the force one first, the force balance expression. So what are the forces acting on this diving bell? Well, we have the buoyant forces of the water acting on the air and the diving bell itself, and then we also have the weight of the diving bell and the air. So let's go ahead and write that. We're going to start with force balance. Okay, so we all know F equals ma. I'm not going to bother writing that. But let's start with our gravity components. So these are the components going downwards. So we have the mass of the bell times the acceleration due to gravity. Additionally, we have the mass of the air times the acceleration due to gravity. Okay, and that's going to be equal and opposite to the forces trying to push up on this diving bell and lift it back up to the surface, which is the buoyant force. Remember, the buoyant force is equal to the weight of the water that's displaced by this diving bell. Okay, so that's equal and opposite to the mass of the water times acceleration due to gravity. That's as simple as it gets. It's our force balance equation, right? Well, we're going to make this a lot more complicated and put these variables in terms of these variables. So let's go ahead and do that now. Well, what's the mass of the bell? Well, we remember that density is mass over volume, right? And this thing has a density of rho sub s, but when it's underwater, it really has an effective density. That is the density of the material minus the density of water. And we proved that in a later video. I'm not going to write out the full length explanation for that again. But know that the density of this underwater is really rho s minus rho w. Okay, that's called the effective density. We'll express that in this video with rho sub e for effective density. Okay, so if density equals mass over volume, we know that mass equals density times volume. So we have the effective density of the bell times the volume of the bell times gravity plus the mass of the air. What's the mass of the air? Well, again, it's going to depend on the density of the air at this depth, but air as a gas doesn't exactly work like the material does underwater, having an effective density, but the density is going to change by our ideal gas law. So if you remember the ideal gas law, we can derive from the ideal gas law that the density of air is equal to pressure times the molar amount of air over R, the gas constant, times T, the temperature. Okay, well, let's go ahead and I'm going to substitute this in right now. We're going to work more on this expression as we continue expanding this equation. So we have the density of the air, which is Pm over RT, times the volume of air, times gravity. This is equal to the mass of water times the acceleration due to gravity again. Okay, what's the mass of water? Well, the mass of water displaced, that's all the water that would have been in this empty void area, and the water that's displaced by the actual volume of the diving bell itself, right? So let's go ahead and simplify this again. It'll be the density of water times the volume of water displaced times gravity, right? So we've got kind of this like PV or rho VG expression now. Okay, we can continue to work on this. So now, shall we do, I'm gonna keep volume of the bell is constant, right? As we go down underwater, the bell itself really isn't changing. We're gonna assume it doesn't change due to any type of thermal expansion or pressures on the bell. It's a strong material, it doesn't change volume. So I'm gonna keep that. When we go into the coding later, we'll come up with a number for the definite volume of this bell, but for now, V bell works just fine. So let's keep writing this equation out. We get the effective density of the bell times the volume of the bell times G plus, okay, so let's work on that Pm over RT times V times G again. What is the pressure at this depth of the air? Well, remember from our previous videos that pressure is rho GH. Okay, so I'm going to rewrite that. I'll write that here just out of the way. Pressure equals rho GH, and this is the rho of the fluid that we're in. Okay, so the pressure here, and we're going to go into this with our pressure balance equation here, but the pressure here of the water must be equal to the pressure here of the air, right? So the pressure of the air is rho GH. Okay? Where H is the depth down. But depth to this level right here is depth of the bell, depth to the bottom of the bell minus Z. So I'm going to go ahead and replace H with D minus Z. Okay? Now that should work a lot better there. Okay, times the volume of air. Well, the volume of air is, at this depth, it's going to be the cross-sectional area times the height of the cylinder, right? So we can multiply this. We have the cross-sectional area, we'll call that A, times, what is the height of the cylinder? Well, it's H minus the amount that the water is encroached, right? So H minus Z. Okay. Times G. Can't forget G. And let's expand the other side of the equation again. We have the density of water. Okay. The volume of water. Well, the volume of water that's displaced is going to be equal to the volume of the air inside plus the volume of the diving bell, right? Times G. Well, we just found out the volume of the air inside the bell. That's this right here, right? Ooh, that was rough. We'll do that. Here you go. That's the volume of the air inside. Oh, you know what? So I made a quick mistake here. We actually don't need to include the volume of the bell here. That's what was bothering me. The reason we don't need to include the volume of the bell here in the water displaced is because we've accounted for it with the effective density of the bell itself. Remember, when we account for the effective density, we're subtracting out this term already onto this side with our effective density. So really, we don't need this here at all. We've already accounted for that. We don't want to double count it. That's better. Now the volume of air, like I said, is this. So we can go ahead and put that in there. We get, what is it? A times H minus Z times G. Okay, I think that's as far as we need to go now before we go to the computer. So, at least with this force balance equation. So I'm going to lock this in as our force balance equation. We'll take this to the computer and with our next equation that we're going to solve for here. Okay, so the next one, like I said, is going to be a pressure balance equation. So not only do the forces balance, but at the surface of this water level here, the pressures balance. We know that because, I mean, the water doesn't move at all. The force down on it due to pressure must be equal to the force due to pressure coming up, just like we just showed here. Okay, so pressure balance. We already said that the pressure at this depth here is rho GH. And we need to come up with a new expression here that shows that the pressure of the air equals the pressure of the water. Okay. So if we count this as our expression as the pressure for the water, we need to show that this is equal to pressure for the air. Well, what's the pressure of the air? We can use the ideal gas law once again. This is the true ideal gas law. Remember, PV equals nRT. Even though the air compresses, so the volume changes, the number of moles of air in the valve stays constant. Okay, so that's an important thing to remember, and that's what actually allows us to make this whole thing work. So let's go ahead and rewrite pressure as nRT over V. Okay, so we need to think about how the pressure changes from the surface of the water before it's even dunked into the diving bell's air all the way down at the bottom. In the initial state, pressure equals nRT, and V just equals the volume of this cylinder, which is the area times the height. But in the final state, which is where we're at now, the pressure equals nRT over the cross-sectional area, but the new H value, I'll say, is H minus Z. Right, it's been compressed. It's a smaller, I'll say, cylinder of air inside there. Okay. Now, if you notice, we have two things in common with this equation. If we write them both in terms of nRT, this one we get nRT equals P naught times AH, and this one we get nRT equals P times A times H minus C. Let's go ahead and do that. Excellent. Okay, well, this is interesting because we actually know what P final is. This, I'm calling this P final now, I guess. Or maybe I will keep it less confusing. We know what P final is. P final is equal to rho GH. Okay, and oh, we can't forget, before we substitute this in here, remember H here isn't the total depth D, but it's D minus Z, right? Because it's this depth. So this is, before we forget, that's D minus Z. Okay, so we know what P final is. It's this. It's the same pressure as the water, rho G times D minus C. So what we can do is take this expression we just wrote here and substitute in for P final this value of rho G D minus Z. We get a new equation that looks like this. P naught times A times H equals pressure, which we just found was rho, the water, density of water, times G times D minus Z times A times H minus Z. That's this half of the expression there. We notice that our A's cancel out, and that's all that cancels out. So we're left with P initial times H equals the density times G times D minus Z times H minus Z. Okay, and that is our final pressure balance equation that we're going to take to the computer with us too. So we have two equations here, and you can see why this is possible to solve by hand for Z. With this, we'd get a quadratic function, and same for up there. We could set some things equal to each other and probably solve with a system of equations if we had enough known values from our problem statement. But this is going to be a heck of a lot easier to write a few lines of code for and solve. So we're going to take this equation and this equation over to the computer, and we're going to go solve them. So stick around. Wait for the jump cut, and I'll see you in just a second. Thanks.
What is up, guys? Thanks for joining me back here at the computer. We're going to keep on chugging away at this problem. I actually included the whole problem here on the screen just so we have an idea of what we're actually solving for. We came up with the equations last time at the whiteboard. I've got those rewritten right here. I'm not sure if you can see those on my other camera, but they're just for our reference. We'll put those back into the code. So remember, we came up with our force balance equation and then our pressure balance equation. So what this problem then gives us is a bunch of these variables. We've defined them now, give them numbers, and then we're going to be solving for, you can see here, calculate the submerged depth. So that's D in our equation. at which the diving bell and the air entrapped within the has zero net buoyancy. At this depth, how far into the cylinder does the water encroach? And that's the variable z. So every other variable we've put in these equations is defined somewhere in this problem, or we'll make a definition for it in the code. And we're just going to be solving for d and z. And we're going to do that with the scipy.optimize.root function to find both of those. All right, so let's get going. Hopefully you should be able to see me both here and here. And yeah, all right, let's do this. So we'll start. We need to always import our NumPy, and then we'll import scipy as well. Okay. All right, so let's go ahead and start defining all these variables. So the ones given in the problem are as follows. We have an open bottom steel diving bell with density 7850. Okay, so let's go ahead and do that. So the density of steel, we'll say rho sub s is equal to 7850. And I'm just going to keep these as, I'm going to put the what do you call them? The units off to the side here in text, just so we don't forget. So that's kilogram per meter cubed. Okay, is approximated as a cylinder with inner radius 1 meter. Oh, and obviously this is going into water. They're probably not going to give us that, so let's go ahead and we know the density of water is 1,000 kilograms per meter cubed. Okay, and what else do we know? Inner radius of 1 meter, so we'll call that R1. 1, that's meters. Inner height of 5 meters. So H we'll call 5. Uniform wall thickness of 1 centimeter. So we'll say thickness is little t. And that'll be 1. We want this in meters because that's what the rest of our units are in. So instead of 1 centimeter, 1 times 10 to the negative 2. And that's meters. Temperature of 298 Kelvin, so that'll be big T. 298. Okay. For water, actually submerged air entrapped once at this depth. Okay, so that's everything that gives us in the problem. What else do we have here? Well, we should probably define the outside radius as the inside radius plus the thickness. That'll be helpful. Oh, not, there you go. And then what else do we have? So I'm just going to go through our formulas that we've come up with. We have, oh, right, the effective density has been the measurement we've been using. So the effective density, remember, is just the density of steel minus the density of water. Okay, we have, I'm going to come to the volume of the bell last. I'm going to make sure we have all these. Oh, we need to define gravity. Okay, so that's 9.81, and that would be in meters per second. Okay, we don't know D, we don't know Z. M, the molar mass of air. I have not come up with that one yet. Let's do a quick Google of that. Molar mass of air. Okay, 29-ish grams per mole. So we need this in kilograms per mole. It'd be 29 E negative 3. And that is now in kilograms per mole. Okay, then we have, oh, the gas constant R, we'll need that. Gas constant R, 8.314. Then we've already defined temperature. For water, HH. Okay, I think the last, oh, and then pressure initial. We'll need the atmospheric pressure, so we'll just call that like P in initial is 101,325, and that's obviously in pascals. Okay, now I think all we need, we'll just do the area now and the volume of the bell because we've used those a few times in our formulas. So the area is equal to, actually, let's do the volume. Well, now let's do the cross-sectional area, the inside of that container is just going to be, what is it, pi r squared, right? And then we're using R1. So NP to pi times R1 squared. Okay. And then we just need the volume of the bell. Use that in our equations too that we came up with. Okay, so the volume of the bell is going to be the volume of the shell walls plus the volume of the end cap. So the shell walls are going to be, it's pi times the difference in radii squared times the height, right? So we have np dot pi times, we need the difference between r2 squared and r1 squared. So that'd be r2 squared minus r1 squared, okay, times the height plus, now we need the end cap volume. So the end cap volume is just going to be pi times r2 squared, right? It's the outer cap times the thickness of the container. Pi times r2, little r, r2 squared times the thickness. Okay, and that should be good. I think that's all the variables we'll need. I guess we'll find out if we don't have enough. Okay, so now we can start solving this problem. So the scipy.optimize.root function is going to basically have us, we'll have to input a function that it needs to find the root of, and then a guess for that function. So let's go ahead and come up with that function first. So we're going to define a function like f by a vector. And the reason we're doing this is because the scipy.optimize.root function can only take in like a single variable function. So we need to define this function f by only vector. But remember, we don't have d or z. So vector is going to be defined by two variables, d and z equal vector. And that's going to be our workaround for that problem. Okay, so what do we have? We have two equations we came up with. Equation 1, and we came up with equation 2. Okay, and I guess it's hard for you to see. I rewrote our equations right here on the board. Can't see them there. Right here, this was our force balance equation, and this was our pressure balance equation. So I'm just going to go ahead and type these equations in so that we can optimize them in the scipy.optimize.root function. And when we type these in, I've set them equal to equation 1 and equation 2, which really means we're going to set them equal to 0. So I need to take all the terms, move them to one side, and then they'll be set equal to 0. So when you see this, but then a negative version of this, that's why. Okay, so equation 1 was our force balance equation, and I'm just going to copy it straight from what we found on the board. So we have the effective density, underscore, there you go, times the volume of the bell, plus, we have that whole term for the density of air at a given depth. I really don't want to type that in. I'm going to come up with another variable for, or like another definition for that in just a second. So bear with me. We're going to call this density of air. And I know we haven't defined it yet. I'll do that in just a second. Okay, so we have that density of air times then the area that we found times the quantity H minus Z. Okay, then we subtract over to the other side that density of water times area times H minus Z. So we have then density of water times A times quantity H minus Z. One thing you'll notice here that is slightly different than the equation we found on the board earlier is there's no gravity in this. I simply factored it out. There is G on every term on both sides of this equation, so we don't need to include it. It's just been factored out. So if you are noticing that it's missing, that's why. Okay, and then let's go ahead and define that density of air at a given depth before I forget that. So rho underscore A, density of air, given depth is equal to, and then it's going to be that whole middle term. So we said it was the quantity, the density of water times gravity times the quantity d minus z times molar mass of air divided by r times t. I suppose we should put that in parentheses there. Okay, so now that equation one should all work out. I don't see any little yellow squiggles. We're good. Equation two now is a little bit simpler. That's the pressure balance equation. So we have P initial times H minus, we're going to subtract that whole other term to the other side, the density of water times gravity times the quantity D minus Z times the quantity H minus Z. Okay, and that's our second equation. And then obviously when we call this function, we want to return an array for the SciPy to optimize that root function of equation one and equation two. So it's going to be equation one, equation two. Oh, that is not equation two. There we go. Okay, I think that should work out for us there. Okay, now all we have to do is carry out the SciPy to optimize that root function. So we need to, like I said, the SciPy to optimize that root function takes a guess first for the variables it's trying to solve for. Obviously, we're trying to solve for d and z. That's the function, or that's the variables the vector function is defined by. So we need to make a guess for d and z, excuse me. So I'll just call this guess, and that will equal, let's see, so we need d comma z. Let's say we're going to guess at 2 meters down, the water seeps in by 3/4 of a meter. Who knows? It doesn't really matter. We just need a guess for the function to start. Okay. Now I can do the root function. Okay, and then we're calling the function f, and then we're using our guess. And then let's see what this spits out for us. See if I did it right. Okay. And then, so we got the solution converged. We're interested in this x values. We're gonna do this really quick. We're gonna set this equal to a variable. Say it's like the solution. And then we can call that x value, just so we're not looking at a whole solution. Yep. Okay, there we go. And then there's our solution. So what this means, the interpretation of the solution is that at a depth of d equals 71.81, the net, or the buoyancy is net zero. Okay, that's sitting there. And then at that point, the water has creeped in a value of z, which is 4.24 meters approximately. Okay, so I think that's it. I think we've solved the problem. Thanks for joining me back on the computer, and I'll see you next time. This is the end of homework 2 part C. I know, so sad. So I'll see you next time for homework 3 part 1. Thanks for joining me. Have a great rest of your day. See ya.